area of a triangle. You already know one formula: base times height divided by, how do you 1/2 times base times height. Is that I write it? That's one formation, right? So here's slightly different formation. Suppose we don't know that. You have, does it look like right triangle? It does. So I'm gonna change it like this. So it doesn't look like a right triangle, right? So I'm gonna write it here A, here's a B, here's a C. And you will label this side, let's say this side A, and that side B. Is that right? And that side little c. So which one is a base and which one is a height here? C seems like a base, the bottom part of here. What is the height here? B is not quite the height. Yeah, whatever that's in here, that perpendicular altitude of that vertex C over the line AB, that's the height. Does that make sense? Yeah. So we want that as a height. How about you turn that triangle around and put that side, little a, as horizontal in there, and that can relatively to base, right? But moving around triangle like that doesn't change the area, right? The same thing. So if you go over here and looking over that side, you're going to say that A is going to be my base, whoever's sitting over here, right? And then it's going to be different height, and so on. Okay? So the base and height is a relative term. Wherever you're shooting, and that's going to determine what the base and height is. Okay? But we're going to bring in angles here. Adrian, can you? All right, so yeah, she's outside. Okay, so since the book uses A and B, I'm going to put theta over here. That's going to be the angle. All right, so how are we going to use that? So that's the area here, area of this triangle is 1/2 is still there, and A times B. Those are the two adjacent sides of this non-right triangle, general right triangle, right? I'm beginning to use this term adjacent. In the right triangle, there is only one adjacent side, right? The other one is called hypotenuse. But here in this general triangle, there's no hypotenuse. C is not hypotenuse. It's just an arbitrary triangle. We call C opposite side of the C. Is that right? Yeah. And this A and B actually adjacent sides, two adjacent sides, right? So the area of this triangle, and for that with that angle in there, is a 1/2 times two adjacent side of that angle times sine theta. Okay? So the following clause is not necessarily the formula, but to show you that what this general trigonometric definition is about, where theta is allowed to be 0 and 180 degree. You're not going to have an angle that is greater than 180 degree in the triangle. Is that right? Right? Yeah. The sum is supposed to be 180, so you can't exceed 180. So theta can be more than 90 degree. That's the whole point. Right? So if I put sine of 120 degree, do you know what that means? Sine of 120 degree. You go to the second quadrant to you here, and then draw that right triangle. Remember how you compute the sine of 120 degree? That exact value, without even changing anything, sine or anything, that goes right here. Sine theta, right? So if theta remains in between 0 and 180 degree, that covers first quadrant and the second quadrant. Is that correct? In that first quadrant and second quadrant, the sine, SIGN, all of the sine value remain positive or negative? Positive all the time, right? So we expect the area to be positive value, right? So that makes sense. Sine appears there exactly in the raw form like that, and it's going to be always a positive as long as your angle remains 0 and 180 degree, correct? Can you make sense out of this formula? Making this angle bigger than 90 degree, and this whole thing remains positive, right? Have a question? Yes. All right, this is a formula. How do you remember this formula? It is based on 1/2 times the base times height. But we're using the trigonometry, and there is a sine area. Sine is related to the area. And what are these two? AB, adjacent side of the angle you're looking at. Angle of interest. Okay? All right, let's look at examples. All right, here I am showing a triangle, and I am hiding the formula. So let's use this opportunity to try to remember what the formula was. So here's an example. We have two sides given, an angle in between. All right? Does that fit into the formula, I think? What is the area of this triangle? So let's remember the formula. 1/2, right? It's based on the first formula, 1/2 the base times height. So that's why there's 1/2. What are the two things we multiply? In the formula was A times B, right? But in this, nothing is labeled here except the vertices. There's going to be sine, right? There's going to be sine of what degree? 120 that we're looking at there, 120 degree. And what are the two sides we're multiplying? Adjacent sides of 120 degree, right? So we do have these two adjacent side, 120 here. Right next to it, there's 3. We don't use this side. Okay, opposite side. Two adjacent sides. So there's a 10, there's a 3, right? Correct? So if you can calculate the value of sine 120, then that's it. But since it's given the dimension, centimeter, and we know this is area, right? So what could be the correct dimension of this number in here? Centimeter squared. Area of something, centimeter squared. Okay? So since I know you can calculate the sine of 120 degree, and I want you to do that. Draw the circle again, right? Locate that triangle quickly, and what is the angle in that right triangle, and things like that, right? So here's an exercise for you. Compute sine 120 degree in exact value, not using the calculator. Exact value, and then we're going to calculate an exact value of this. Right, I got the value of sine 120 degree being positive root 3 over 2, right? If you sketch it like this, it's related to the right triangle with a 60 and 30 degree angle. So if you identify coordinate, like we said, in the second quadrant, sine value is going to have a positive y coordinate, right? So it's a positive root 3 over 2. That's the value of sine of 120 degree. Make sense? That raw value goes into that here. Then we can calculate the area. A here, capital A, is 1/2 times 10 times 3 times, what is sine 120? Root 3 over 2, right? That's the value. Not turning this into a numeric, you calculate an exact way, is probably what Weber science sometimes wants. If it wants numerical value, it says round to 2 decimal places, something like that. So you have to simplify in an exact way, okay? So there is a question. Okay, so what is this thing? Anyway, I have canceling of 5, and there's no other cancellation. Is it 15 times root 3 divided by 2? Fair enough? Square centimeter. That is the area of this triangle. So a new formula. All right? So, any question? It's exercise number 56. Alright, the same sine 60 is going to be used, and we know what that is. We just calculated it. We just used it, actually. Root 3 over 2, and I also sketched that special triangle. From there, you can figure that out. Or you can just calculate the area of this one and multiply by 2. That's if you copy the two of them, you're going back to the equilateral triangle. But it's not the 10, so you have to be careful. We're just using the ratio. Anyway. So half times the 2 sides 10, 10 and sine 60, right? That's the formulation. And the exact value is 25 times root 3. Okay. For some reason at this point, whenever these two sides are equal to each other, students sometimes mixed it with the area of a circular sector. Remember the formula? Area of a circular sector? 1/2 times r squared theta versus, what is that we're looking at here? 1/2 times AB times the sine theta. Those two formulas, the area formula, one is not for triangle and the other one is for the triangle, right? Okay, so what you're looking at, if what you're looking at is not a triangle, then you can't use this one. Okay, all right. How about 58 there? I think it's a good problem. Let's try that also as an exercise. It's exercise number 58. Okay, first I convert the 5 pi over 6 radian to degree to handle it better, and that was 150 degree. And you probably figured out by now that if it is in between 0 and 180 degree, and then if we're talking about sine, it's always 180 minus that. So here's the same thing as a 30 degree in there. So I looked at this triangle of a 30 degree of this shape. Here's a 30 degree, and here's a 60 degree there. And numbers go slightly different way, right? So y coordinate is 1, the radius is 2. So sine 150 is 1/2, right? But if you just type on sine 150 in calculator, it's going to give you 1/2, right? At this point, for this type of problem, I'm not going to bother that. You actually draw this triangle, the circle, and this. If I want you to actually do that, I'm going to let you know. Draw the circle and do it. And here is not the main point. But I'm doing this in here to use every opportunity just to keep reminding you of the sine and cosine is about the circle, and you need to get used to it. And that's why I'm doing it this way. Okay? But so sine 150 is 1/2, and if you plug it in here, 24 is supposed to be 1/2 into a times a, both are the same, sine 150. So if you solve this algebraic equation, the exact value is root 96. And if you type root 96 in Weber sign, it should take it as a correct answer. You don't have to pull out square part and simplify like that. This will be sufficient. Any question about this problem? Is that all right? Now, we question ourselves, why is that, right? Why is the area like that, right? I guess more than half of us want to know why the formula works like that. So I'm answering. The idea is embedding this triangle into XY coordinate plane. Did we do something like that before? I think we did something like that. Well, I think I did it one time. I don't remember what that was. But here's one example. And we're going to do this again and again, and you'll see this a lot. We're going to embed this triangle and situation into XY coordinate plane. Coordinate geometry, right? So here's why the formula works like that. Okay, here's a triangle. Let's say some arbitrary shape, and here's a theta, and here's an A and B. Is that all right? I'm going to put B and A here. That's easier for me to rotate around. Sorry for changing it. This really doesn't matter, but easier to see. A and B in here, any orientation. Rotate it around and things doesn't change the area of a triangle, right? So I'm going to embed this one nicely to XY coordinate. Well, I should have prepared it better. I'm changing it again. Theta is over here. Let me draw this triangle again to emphasize it is cover obtuse triangle. That's Should have thought better. All right, so here's a situation. Here's here's A, and here's B, and here's a theta, and here's the final side there. Sorry about that. So this is triangle, and theta looks like a more than 90 degree, right? So we're going to rotate around, and that point is here, and that's going to be that side with the length A. Can you imagine you rotate it around and put in there, and that angle theta here's a vortex C goes right there. Is that all right? And then the side B is going to be somewhere over here. Side B there. And that's the angle theta. Is that okay? You rotate around and put your triangle into this position. Side A goes to that side there. Okay? Now, here is, if you look at it like this, base is A, right? Base is A. And what is the height of this triangle? The answer is not B, right? You look at this is a base, and look at the opposite vertex, and you have to think about altitude toward to the base, this short baseline. You can't draw from here to there, 90 degree line, right? It's impossible in that picture. And you have to extend this baseline in here, which is whole x-axis, and you have to go toward to that, like this, to 90 degree. And that serves as the height of this triangle. If you're looking at this as a base side, and that's going to be height, that's easy. But if you're looking at here, this is my base, and what is going to be the height is the opposite side and projected down, and that's the height here. So that's the height, right there, height, H. We don't know what that is. All we know is A and B and theta, but we want to know that guy, H, right? So that we can write down the area. So at this stage, if we use H, how does this area look like? 1/2 times, what is the base here? A. What is the height? We named it H in here. If I can rewrite this H in terms of A and B and theta, these are the three pieces of information given, and I'm done. H is not the part of information given, right? So the goal is that rewriting this H in terms of these three things, A, B, theta. And my favorite thing is draw a circle out of this one. This point involves this H definitely, right? So I'm going to draw a circle like this. See that circle? Like that. Happy enough? That's the circle with what radius? B is the radius. Thank you. That's so the radius is B squared here, right? Correct? Right. And here's x coordinate, and there's y coordinate. And these x coordinate and y coordinate is related to sine theta and cosine theta, right? Correct? Yeah. But how is this H is related to x and y? H is y. Not even changing the sign. H is the length, and y in the second quadrant or first quadrant, they're always a positive, right? So you don't have to worry about plus sign and negative sign. So the second thing is that in that context, H is y. It's not this important part. Correct? All right, now how are we going to connect this H and y and theta? How is this x and y is related to the theta? The definition, right? What is the definition of sine theta? Close. The y over radius r here is actually b. That's right. And y is actually h, right? You see that already h and theta is connected through the trigonometry. But I'm just going to write down the remaining trigonometry. Cosine, x divided by b, correct? Tangent, y divided by x. Okay? But it turns out this is what we wanted to know, because y is our h divided by b, and this connects h and b and theta. H is the only thing that we created, we labeled, and B is given and theta is given. It looks good. So what do you want to do at this stage? You solve this equation for, let me write it again, sine theta equals H divided by B, right? We want to solve this thing for what? H, right? We want to get rid of H. So what is H? B times sine theta. B is given, theta is given. I can plug it in here and calculate this H, right? So here's the final thing. We're going back to our area formula, A, right? What is A? 1/2 times base times H, right? Now we have a different expression for H, which is B times the sine theta. So 1/2 times, I'm going to use parentheses to show you where it's coming from, B times the sine theta. That H is replaced by B times sine theta, right? So what is B times sine theta? It's really the height of this triangle. It doesn't matter if it is an obtuse angle so that it's over there in the second quadrant and the first quadrant. Sine theta will pick up the correct sign, SIG, positive and negative, and a positive value, and go in there. Did you recognize this is a formula that we've been using? 1/2 times A times B times sine theta. Okay? So if you put it into coordinate geometry, and things get a lot clearer and easier, and often you take care of different cases of, obtuse and acute triangles. That's why. Did that explain why the formula works like that? So, but you're not